want to introduce a new concept, the concept of differential operators. Let's look into that. We have a second order constant coefficient linear ODE in the form a y second plus b y prime plus c y equals to 0. And what we want to say is that if we have a function v and we apply the left-hand side, we retrieve a new function. So we want to write something that goes from the bubble on the left, phi, to a phi second plus b phi prime plus c phi. Both of them are functions of time. So we want to construct something that takes a function and returns a function. We call this type of thing operators. Operators are functions of functions that return you a function. In this case, we want to introduce the operator that takes phi and returns a phi second plus b phi prime plus c phi. We call it a differential operator for the simple reason that we're taking derivatives in the operator. We can have integral operators if we were taking integrals. There are a variety of operators, but we're going to be focusing exclusively on differential operators during this course. Remember that the differential operator of phi is a function of time itself. So we can write it either as L square parenthesis phi, in which case we are thinking about a function of time, or L square parenthesis phi round parenthesis t. In this case, we mean that we have applied the differential operator to phi, and then we have computed it at t. We also want to look at non-constant coefficient ODEs, second order, homogeneous, but non-constant coefficients. So we don't require p and q to be constants anymore. So we have this new ODE that is y second plus function of t y prime plus function of t y equals to 0. And we associate to this a differential operator. Is an operator that takes as function phi and returns phi prime plus p function of t multiplied by phi prime plus q function of t multiplied by phi. And it's defined over an interval of time. T can change between alpha and beta. Either of them can be infinity, so alpha can be a real number or minus infinity, and beta can be a real number or plus infinity. And we're anywhere in which our differential operator makes sense to be computed, it's inside this interval. So we go from the ODE, that is y second plus pt y prime plus qty equals to 0, we go from there to the information that the differential operator of y computed at t is equal to 0. These two are just the rewriting of the same information. We have defined the differential operator as the thing that is the left-hand side of our ODE, and we want to look for a solution that has it equal to 0. There is, for these cases, an existence and uniqueness theorem. Actually, even in the non-homogeneous case, we have, and we're not going to prove this, that if you're looking at the problem y second plus pt y prime plus qty equals to g of t, and you have the two initial conditions that we expect, so y at t naught equals to y naught, and y prime at t naught is equal to y naught prime, where p, q, and g, so all our functions of time, are continuous on an open interval that contains the t naught we're looking at, then on that open interval, there exists a unique solution. The information that we have here is existence, uniqueness, and the interval over which existence and uniqueness are satisfied. So this is a strong theorem. It's the correspondence in second order ODEs of the theorems we have seen for first order. What is the difference here? Well, the main difference is that we now have a second order derivative and a second initial condition. We're going to build on the theorem we just introduced to construct a bit more. We want to look at what is the shape of the solutions. So we're going to start by a superposition theorem. If we assume that we have two solutions of a differential equation, so we have y1 and y2, both solutions of the differential equation y second plus pty prime plus qty equals to 0. So we have taken the differential operator of a second order ODE, possible with non-constant coefficients, but we want it to be linear. If we have two solutions for this ODE, then C1y1 plus C2y2 is also a solution for any value of C1 and C2. And we can write it as C1 plus C2, C1y1 plus C2y2. When we apply the linear, the differential operator to this block of things, we retrieve 1 for any value of C1 and C2. It's called superposition because we have two information and we can superpose them and still have the same result. And it follows, we can prove it by just direct computation. So we are taking the differential operator of C1y1 plus C2y2. Then we have this long thing, is the second derivative of C1y1 plus C2y2 plus pt first derivative of C1y1 plus C2y2 plus qt of C1y1 plus C2y2. We compute all the derivatives because of linearity of the derivative with respect to the sum. We can just distribute things down, we can multiply everything away, and we have some terms with y1 and some terms with y2. So we restructure things away, and we can write it as C1 multiplied by y1 second plus pt y1 prime plus qt y1, and this is a block, plus C2 multiplied by y2 second plus pt y2 prime plus qt y2. These two blocks that we have, these are exactly the differential operators applied to y1 and y2, so these two blocks are equal to 0. And the fact that they're multiplied by constants doesn't matter, they're still equal to 0. So indeed, if we are applying the differential operator to a sum of C1 y1 and C2 y2, we are retrieving 0. In case you're interested, the key elements that we're using through this proof is linearity of the differential operator that we're looking at. So the ODE is linear and the ODE is homogeneous. Once you have these two elements, you can do this trick. You don't have to restrict yourself to the second order. It just becomes more cumbersome to show it. So now that we have the fact that given two solutions, we have infinitely many solutions, we'd like to determine the constants in front. So the C1 and C2. And we do that by using the initial conditions. So we need that at T0, C1 y1 plus C2 y2 is equal to y0. And again at T0, C1 y1 prime plus C2 y2 prime is equal to y0 prime. When does this have a unique solution? Well, it's a two-dimensional linear system. So it has a unique solution if the determinant of the coefficients is different than 0. So we will introduce this W, that is the determinant of y1 computed at T0 and y2 computed at T0 on the first line, and the derivatives on the second line, so y1 prime computed at T0 and y2 prime computed at T0. So the determinant in a two-dimensional matrix is the product on the first diagonal minus the product in the other diagonal. So we retrieve that W is equal to y1 computed at T0, y2 prime computed at T0, minus y1 prime computed at T0, y2 computed at T0. if this thing is different than 0, then we can find unique constants that satisfy our equations. We can actually write them explicitly. They are y0, y2 prime computed at t0 minus y0 prime y2 computed at t0 divided by capital W. And C2 has a similar structure. We just replaced y2 but by y prime, but by y1. You don't have to learn these two equations for C1 and C2 by heart, but you need to know that there is this determinant W that needs to be different than 0. And we're going to look a bit deeper into this topic. So we have defined W as the determinant of this matrix in which in the first line we have y1 and y2, and the second line we have y1 prime and y2 prime, and all of this is computed at t0. We can define the Wronskian as the determinant of the matrix in which the first line is y1 and y2, and the second line is y1 prime and y2 prime. This is a function of t because y1 and y2 are both functions of t. So we're taking a determinant of a matrix of functions of t. So now W depends on y1 and y2, and once you have computed it depending on y1 and y2, still depends on time. To compute the Wronskian at a given time t0, we write it as in a similar way as we did the differential operator. We write W squared parenthesis y1 and y2, round parenthesis t0. This is our indication that we are taking y1 and y2 as functions of time, W of y1 and y2 is a function of time, and then we compute that function at a specific time. Now that we have constructed the Wronskian, we have a theorem about it. It states that if we take two solutions of a linear homogeneous ODE, second order, with two initial conditions, then there exists a unique choice of C1 and C2 such that y equals to C1 y1 plus C2 y2 satisfies the initial conditions. And this choice is unique, exists and is unique, if and only if the Wronskian is different than 0 at t0. So if you have two solutions, you can find the coefficients of their sums only if and only if the Wronskian is not 0 at t0.